So many thanks for the invitation, and also because the timing is good, I would say. At this moment, the European Union and the European Commission has provided a communication on the Repower EU, and I would like to use this to set the scene, as you already announced, Thea, to the discussions of today. And maybe also to give some hints on where we as biogas sector would like to go to in cooperation together with all the DSOs, TSOs, gas grid operators, and everybody involved also on the gas quality side. So let me go first to where we are. The next slide, please. A little bit first on the EBA itself. So we are an organization comprising now, actually, this is already outdated because we are growing very fast, over 200 companies and associations directly related to the EBA, representing around about 7,800 stakeholders within the 36 countries in Europe and beyond. So with that, we are actually one of the larger associations within Europe, although we are still seen as small, and I'll come to that a little bit later. Next slide, please. So where are we today? Today, we produce 18 billion cubic meters. That is as of 2020. Those are the numbers. We are compiling 2021 at this moment, but 18 billion cubic meters of energy on the biogas side. 3 billion cubic meters, just a bit less, but 3 billion cubic meters is biomethane. The remainder is biogas for CHP, so electricity and heat production. But when you look at the various reports which has come out in the previous, actually 2 years, we see that there is a consensus about the potential for 2030, that is around about 35 billion cubic meters, and then reaching up to 100 to even the latest report from Engie, 160 billion cubic meters on the production of biomethane. That is not biogas, but biomethane. Now, on top of that, we can even produce e-methane, so combining the CO2 with hydrogen from peak loads on the electricity net, and that would actually help another part of biomethane production, an extension of 60% on top of the already between 100 to 160 BCM. So with that, we can be anything between 30 to 40% by 2050 alone by biogas or biomethane. If we add the e-methane part, we can be even a larger share. By 2030, which is of course closer and nearby, we can already do 10%, depending, of course, all this is depending, of course, on the total gas consumption. Next slide, please. Now, what we see here is the recent natural gas pricing has put us already on the spotlight, and for reason. I just checked this morning. The TTF went up a little bit to 93 euros the megawatt, but we can already produce as of 55 megawatt per megawatt hours, which is already cheaper. And of course, it's all depending on type of feedstocks and size and location where you are, so the prices are differing, but we can already produce at a lower price. This is not taking into account any CO2 cost price of fossil natural gas. As you all know, we are hugely dependent on the gas supply from imports, and there we can put something valuable on the table. We can produce locally as well as provide a significant portion of the gas supply, the renewable gas supply in future. Now, questions we get almost daily is, sure, you can produce, but is it sustainable? The simple answer on that is yes. We can produce that from food waste, from industrial wastewaters, wastewaters, municipal wastewaters, from agricultural residues, no use of monocrops, but do use of course, sequential cropping in combination with carbon sequestration. Next slide, please. Now, on the 8th of March, the European Commission came out with the Repower EU plan. And within that, they set a target of 35 billion cubic meters of biomethane by 2030. This means that we as industry, but also all people and companies connected to this, need to ensure that we are ready to actually make this happen. For the industry, this means that we will, and we are aiming for 5,000 extra installations in the coming 8 to 9 years. 5,000 sounds a lot. It is not that many. Germany already did 6,000 installations, be it smaller, but in 9 years' time. So in the whole of Europe, put in 5,000 installations is doable. And again, I said in the very beginning, we are sometimes looked at as small. That's because we are localized. And that just gives some food for thought. Being localized is not bad, because everything what we do in scaling up often end up with a lot of downsides. Of course, the obvious example is the fossil industry, where we scaled up humongously, and now we are set with all the downsides with it. So localized production, providing localized jobs and integration with, say, for example, organic fertilizers and the whole integration within society is very important. Next slide, please. So where can it be used? I probably do not have to tell you, because you're all gas experts. So here we produce, or it can be used in the buildings industry, can be used in the industry itself. It can be used for dispatchable power, of course, and not to forget also for transport. Next slide. So what is then important? And that is the gas infrastructure. The gas infrastructure we can save by utilizing the gas infrastructure. We can save Europe 217 billion euros per year just by making sure that we keep the gas infrastructure there. That is of the utmost importance. It means that we also need to make sure that we think on how to make sure that it is all easy to use. Easy to use because we have in every country, there is almost different set of rules for injection of biomethane. And it becomes a little bit of a problem, I have to say. In one country, Denmark allowed 0.5% of oxygen and proved to be possible, whilst in other countries, Germany, it is very low. I don't have the number for the injection in Germany, but I do know that in the interconnection point cross-border, it is even lower than the injection point within Germany itself. What we need to do is we need renewable industry. We need renewable gas. We cannot afford to set rules which are trying to, say, mitigate the risk to 100% risk mitigations, while it doesn't bring us anything. So we need to be pragmatic, and we need to harmonize across Europe, also on the oxygen content. And just to be fast and to give you some ideas, what we think is needed is to set one rule for oxygen content throughout Europe, and ensuring where we think there might be possible problems in the future for some gas storages, has centralized oxygen scavengers at those places. Next slide, please. And that's it. I thank you very much. I probably know that there are some questions with regard to that, but I believe that we can answer that at the end, Thea.
Thank you very much, Harmen. That was a very inspiring inspiration and very, I would say, it's the timing of this webinar. I fully agree is very much it's quite well placed with respect to the discussions you have both in Europe but also in many of the European countries. Yes, I would like to thank you for your presentation, and I would like to for the questions. I can see there are a few questions coming up, but I think for the sake of the time, I would prefer that we take all the Q&A together, if that's okay with you as well. So I would like to say thank you, and then I would like to continue on to the next speaker today, which is Ellen Shoes. Yeah, Shoes. Yeah, because I'm sorry for my problems with pronouncing, but it's a little bit difficult last name to pronounce. I would like to welcome Ellen, who is leading the MARCOGAZ working group on underground storage, and also is convener of the working group 4 at CEN on the TC234. But the purpose today of your presentation is to walk us through the recent report from MARCOGAZ on biomethane acceptance in underground storage facilities. Helene, the word is yours.
Thank you very much. Good morning, everybody. It's my pleasure to be here to present you on behalf of MARCOGAZ working group on underground gas storage this position paper about biomethane acceptance in UGS. Next slide, please. So my presentation is focused on biomethane provided by anaerobic digestion, what some people call the first generation of biomethane. I will present first the approach of MARCOGAZ working group to release this paper and focus on two topics. One topic is trace component of biomethane impact, and the second one is oxygen impact. And after that, I will try to do a preliminary conclusion. You will find every detail in the complete position paper, freely available on MARCOGAZ website. Next slide, please. So methanization produces biogas, and biogas is purified to become biomethane. Biomethane is very similar to natural gas, but some trace components may be specific as terpene and siloxane, and some trace components are similar to natural gas, but maybe a bit risky as HEP or heavy metals. And some minor components could have higher content than in natural gas, as CO2 and oxygen, of course. On the other hand, underground gas storage facilities are specific infrastructure. Why? Because in the reservoir, gas could be in close contact with underground water, especially in aquifer reservoir. Because wells and flow lines, which are piping from the wellhead to the gas treatment units, contain wet and acid gas. And because some of them may be operated in a very high pressure, till 260 bars, and this pressure, of course, increases the reactivity of minor component. So working group storage in MARCOGAZ share results of past experiment, of research program, and all the reference of this experiment or program are included in the paper. The current situation among European countries regarding the oxygen content acceptance has been shared too, and we try to draw preliminary conclusion. Yes, I insist these conclusions are preliminary because, as you will understand later, all the knowledge necessary to conclude is not available by now, but is under acquisition. Please, next slide. So this slide is just to remind the three main types of UGS. The first type is aquifer storage. The gas is trapped in a dome under a cap rock in a porous reservoir, in a porous rock. On the second type, which is a former gas field or oil field converted into storage, the situation is quite similar, but the difference is that oil or gas was previously present in the porous reservoir. And the third type is salt cavern. In this type, some caverns were leached in a salt layer to create a cavern able to store gas. The gas in the subsurface is injected and withdrawn through wells, and these wells are connected to the facility by flow line. On the central facility, the gas is compressed, either to inject the gas or to withdraw it, or both. The gas is treated to remove water and to remove H2S in certain cases. And the gas quality is checked and the gas rate is measured. So that is the main design for UGS. Please, next slide. So now let's focus on this topic of the trace component. Our conclusions are mainly based in a 2016 and 2018 French study. This study performed measurements. More than 200 compounds in the biomethane were searched and around 40 were actually measured. The biomethanes come from different feedstock and processes. Some siloxane were detected, but in very low concentration. Heavy metals were present, but very low concentration too. And in this data set, polycyclic aromatic compounds and halocarbons were not detected. According to this data set, the cryogenic purification or pressure swing absorption process generates a biomethane containing less trace compound than membrane-based purification process. To complement this result, reservoir modeling to quantify the impact on subsurface water was performed. The results are consistent with standard biomethane quality, EN 16723, and the technical report CEN 17238 about contaminant for biomethane. The results of this study were published during the 2018 Gas Award Research Conference and in the 2020 International Gas Research Conference. The project is going on with 500 compounds analyzed and 70 different biomethanes. And this new result will be published in the 2022 Gas Research Conference. On its side, Georg is currently conducting a pre-normative research on biomethane, and we will have detail with the next speaker. And it is expected to produce a wide database on the composition of biomethane and biogas in Europe. Next slide, please. So let's skip to the oxygen impact on the UGS facility. And this topic is a concern for every type of UGS because the trace components is mainly a concern for aquifer storage UGS. So where this oxygen comes from? It is due to air or oxygen injection in the digester to remove H2S. Its concentration could depend on the purification process. For instance, for the, let's say, pressure swing absorption process, the content is 0.1 to 0.3%, that is 1,000 to 3,000 ppm. The possible negative effect on UGS may impact either the equipment or the reservoir. The list is the following: corrosion in wet gas equipment, subsurface and surface sulfur precipitation, generation of black powder, which are pyrophoric iron, accelerate degradation of glycol in dehydration unit, blockage of oxidation of mineral in formation water, and impact on biological equilibrium in porous reservoir. The consequences are dependent on oxygen concentration and pressure. The maximum concentration is an important criterion, but the total amount of oxygen injected in the UGS over a certain period of time is also a very relevant parameter. The impact on a given UGS depends on the material, the reservoir of each facility. For instance, the mineral and the composition of the reservoir water are very important. The oxygen content at the entrance of a UGS depend on, of course, the oxygen content at the outlet of biogas plant, biomethane plant, but also of the specific location of the storage in the gas grid. Next slide, please. So this map, as you see, has different color, is not well harmonized. It's a map presenting the current acceptance of oxygen over Europe. It's quite different. It's slightly different than the map in the paper because we received some clarification from Belgium. And you see that there is a country with in deep blue, which have a high tolerance of oxygen, and some other countries in light blue, which are not, which are less tolerant. The current situation is specific to each country according to its gas grid, to its storage, and to his current facility. And all these rules are not crystal clear by now. And just to remind, the European standard on the topic, the European standards say at the moment 10 ppm, except in case there is no sensitive installation downstream, that means UGS, for instance. In this case, 1%, that is 2000 ppm, is accepted. Next slide, please. So these are our preliminary conclusions. As far as trace components are based on the available data and the simulation modeling, biomethane storage in deep aquifer shouldn't create any significant impact on water quality of the aquifer. But we recommend that measurement campaign should go on to confirm this conclusion and to extend the data set. As far as oxygen is concerned, the situation of each UGS is specific, as I explained. It depends on its reservoir, on its location in the grid, and so a case-by-case assessment is necessary. To remove the oxygen in the biomethane, this removal may be implemented in different locations on the biogas plants, on the grid in different specific point of the grid, or at the entrance of the UGS. This removal of oxygen is not technically and economically feasible by now, especially at the entrance of the UGS, because to inject gas into UGS, very huge weights are needed. But several research programs are going on. They will improve knowledge to assess the impact of oxygen on UGS facility, and they will propose improvement of treatment processes to lower the oxygen concentration at biogas plant or to remove oxygen in the grid. So our target is clearly to be able to accept biomethane in the gas infrastructure, including UGS. But we need more knowledge to do that, and we need to assess the best and the most cost-efficient way to do that. Thank you for your attention.
Thank you very much, Elaine, for a very interesting presentation. I'm certain that we will get some good questions and comments on that one once we are approaching the Q&A session. I think we are great on time. Thank you for that. That's always the challenging thing of a webinar. But I would then like to go, without using the time, then go further on to the next speaker we have today. And please allow me to introduce Timothy Frank Ilson, who is the principal specialist at DNV, who will take us through the results of the research program about biomethane in the gas grid. The floor is yours, please.
Thank you very much, Thea. Thank you. Well, thank you very much for attending. I'm going to talk a little bit about what GERG and TEN, or mostly GERG, are doing on the biomethane study, which is phase 2B. My bit is actually topical because it's mostly about oxygen in underground storage. If you have the next slide, please. So I think you've noticed from the previous speakers, there's an enthusiasm for putting more biomethane into gas networks. And the GERG program overall is intended to reduce the barriers to the injection of biomethane to gas networks. And it's a very large program, but it's quite a small part of it. As Helene was saying, one barrier at the moment is the strict oxygen content restrictions for gas intended for injection into underground storage facilities. So that can drop as low as 10 ppm in some places. So this GERG work is really part of a project under TC 408, which is aiming to justify revisions to the European gas quality standards, the 16723 and 726, I think it is. It's actually the second part now, as you can say, by phase 2B. We did an earlier literature type review looking at the effect of trace biomethane components and oxygen for underground storage. And we looked at aquifers, depleted reservoirs and salt caverns in that one, and had an industry poll really to see what people were concerned about and what issues they thought might occur. And this study I'm just about to describe is a consequence of that review, in that the experimental studies are driven by what the industry said was likely to be a worry for them. So if I start on the experiments, next slide please, thank you. Oh, great. So this is work package 3 for the GERG study. So work package 3 overall is the impact of oxygen and corrosive compounds. So somebody else is doing the corrosion part. This is really looking at reservoirs and non-corrosion impacts, basically. DNV and the University of Pau, the LATEP unit, are collaborating for this study. So it's a good collaboration. We started out doing a rather more in-depth literature review, and we identified a few things that might occur if you put oxygen into particularly aquifers used for gas storage. What seems to happen is you start messing with the electrochemistry of the waters, so you enter change the redox potentials, and the main reaction you get if it's present is oxidation of pyrite, the sulfur mineral, and unfortunately oxidizing pyrite will actually produce local acidification, so the pH value drops. That then effectively starts to dissolve the rocks present. So in a calcite type reservoir, you dissolve the calcite, so that's calcium carbonate, and that really buffers this acidification. So it starts to fall, the calcite dissolves, and then you get a fairly constant pH. That's quite useful because in theory that will stop you mobilizing metal ions, so you don't dissolve a lot of the iron and things out. because those are the things that can give you precipitation and blockages. However, because everything's going to go at a local scale as you push the stuff in and consume the water, you can actually run out of calcite, you consume it, and then you get a feldspar type mineral dissolving. And people theorise that what happens then is you basically run out of oxygen in that area, and that allows pH changes again, and you get aluminium and iron hydroxide start to precipitate, and that's where you get the blockage of a reservoir, and you might have problems injecting. People have had a bit of a go at injecting basically low salinity oxygenated water into aquifers, actually for water storage rather than anything else. But what they found was a distinct buffering effect for 2 years that they did the trial. While we get on with our experiments, we're still carrying on with the literature studies because people are still working in the area, because it's not just for biomethane, but for a lot of other potential injections into reservoirs. Oxygen content is really important. The next slide, please. So what we realised fairly quickly was that we're going to need a really good liquid phase analysis protocol so we can work out what's actually happening, and that we need to develop that before we can start on the main experiments. So between D&V and the University of Powell, we've now defined this experimental program to validate the analysis protocol, which is going to be our base tool, really. And we've got the reagents and equipment all arranged. So what we're going to do is use ionic chromatography and ICP, or inductively coupled plasma optical emission spectroscopy, which are really good techniques for monitoring key chemical species as they change during the tests, because this will be a dynamic sort of environment. We're just about to test that using batch tests. So just to test the protocol, we're going to be injecting air, basically, there's 20% oxygen, into some simulated reservoir waters. We're going to use a pyrite powder, and we've arranged the equipment so we can sample the liquid phase to analyse. So we'll take some out, analyse it, leave it a while, take some out, analyse it, and we'll get on with that in the next month or so. And there's a nice ICP there. Next slide, please. So once we validate our analysis protocols, we've got preliminary concepts for the main test program. So this is actually a reservoir simulation, but effectively. There's two ways of doing this. We can either carry on with the batch testing, or we can do some dynamic column testing. Either will actually work for this sort of study. The slight issue with dynamic column testing is it could actually be quite difficult to detect some of the species in a flowing column. So at the moment we're thinking of using the batch concept, but we're still open to the dynamic one, depending on how the experiments go. On the right there you got a schematic of how we can do this effectively. So what we do is we inject a simulated biogas with varying partial pressures of oxygen, because certainly for underground storage, partial pressure is probably more important than concentration. Temperatures between 20 and 150 C to give us some ideas of temperature dependence. And then we're going to put in the simulated reservoir waters, a solid phase, so we can have pyrite, so we can have oxidation, and the other minerals, calcite, feldspars, etc., to get that interaction. And then we'll measure the gas phase, see what consumption of oxygen occurs, and sample the liquid phase to see what chemical species are forming and what our precipitation is happening. So on the left, we've got what I just said, basically. So the oxygen particle pressure, 0 to 10 is bar G. We're going to try different reservoir compositions, so that'll be interesting. We'll do a literature review, but if people have got particular ones they're interested in, we'll be very interested to hear from you. If people have got samples of reservoir waters, they'll be even more interested. Temperature really depends on the reservoir, but we think we can probably manage it up to 150 C if we had to. And then at the moment we're thinking of using powders just to get good reaction rates, but we could put larger pieces in. And we'll do quite a lot of analysis. We're doing pH, for redox potential and dissolved oxygen, and then sampling for all sorts of different species in the liquids. Next slide, please. If we did flowing tests, which we may well do, in a column, we thinking of setting an experiment set up really based on that of a chap called Berta, who did some similar experiments. And the idea is you set up basically a water in equilibrium with your oxygenated biomethane, and then pump that through a column loaded with, well, if you go to very high pressure, we'll load a core of rock, or lower pressures, you might put a powder in or some sands and things like that with the minerals you're interested in. And then you sample at 4 or 5 points along the column to see how the chemistry evolves as the fluids flow through it. And we'll be measuring similar things again, the redox potential, pH level, conductivity, dissolved oxygen, and running it through the experimental analysis program. So we're looking at ionic chromatography for the anions, and something like ICP-AES or like for cations. So we're interested in the evolution of the chemistry, and that allows us to predict and determine precipitation, because this is all about what's the effect on the reservoir. Next slide, please. Yeah, so as I say, the next thing we're getting on with is validate measurement protocols, start the main test program and push on. That's quite a long test program. We're really interested in what's happening with the oxygen on aquifer water chemistries, reservoir water chemistry, in fact, and the mineral species present, so the actual rocks. As I just said, we're really interested in getting feedback from industry on defining what sort of waters and minerals people have got, to give us an idea what sort of range there is over Europe. Like most of GERGE things, there's a steering committee. So once we finish, or as we go along, we'll be presenting the results to all the different stakeholders in industry and standardization bodies. And we're going to try and work out between us a risk assessment protocol. As Helene was saying, this could well end up being on a case-by-case basis, because reservoirs are all going to be different, and the biomethane is going to be slightly different. But if we can produce a tool or a methodology for doing that case-by-case risk assessment, it means that any particular storage site can define the acceptable oxygen level for that site, and then that will drive their local network requirements. I think that's probably it. I think next slide, I think it's the end. Yeah, that's me done.
Now you're muted, Tia.
We all do it from time to time. We get to put on the sound, what has been taken off. I just wanted to say thank you, Tim. Maybe you could see that from from what I was trying to say. It was very impressive project that is running with GERGE, and it was. We appreciate that you're sharing the results so far with us, plus the ideas you have for progressing this part. With this presentation, it leads us to the final of our 4 first speakers. And I would like to give the word to Annette Møller Hansen, who's project manager at the Danish Gas Technology Center, who will take us through a case study on biomethane in Denmark. The word is yours.
Thank you, Thea. Yes, my name is Annette Møller, and I have been asked by the Danish TSO Energinet and its daughter company Gas Storage Denmark to do this presentation on the situation with biomethane in Denmark. Next slide, please. Just to start with the status on the biomethane in the Danish grid at the moment. There are currently 51 biomethane plants connected to the gas grid in Denmark, and the average capacity often is around 1,500 normal cubic meters per hour, with the biggest being producing almost 16,000 normal cubic meters per hour of biomethane. So relatively big on compared to the average European biomethane plant. And altogether, they produce almost 20 gigawatt hours daily. So that's quite a lot from a Danish perspective. And as you can see from the figure on the left, the biomethane share in Denmark has increased quite a lot over the past few years, increasing from an average share of 11% in 2019 to almost 25% in 2021. But that covers quite large variations over the year because the biomethane production is relatively constant, while the gas consumption is, of course, not. So the biomethane share is not that high in the winter, but during summer periods, it's been up to almost 50%. So that's quite large biomethane shares in Denmark at these times, some time of the year, that could potentially lead to injection in this gas storages in Denmark. Next slide, please. So when we're talking biomethane and gas storages, of course, it's the oxygen we talk a lot about. So I've just pulled some data from some of the biomethane plants in Denmark to illustrate that it's not really a fixed value. As you can see, the water scrubber upgrading plants have a relatively high oxygen content because the water scrubber upgrading process naturally enriches the biomethane with oxygen. So when using water scrubbers, you can't produce biomethane with very low oxygen content. For the membrane plants, they don't add oxygen themselves, but for economic reasons, they generally use some sulfur removal that leads to oxygen being added in surplus. So they also have a relatively high oxygen level, even though they could theoretically produce oxygen, very low oxygen biomethane. For our amine plants, you can see that varies a lot because some of them remove sulfur the same way as the membrane plants, but some of them remove the sulfur after upgrading, meaning that they actually produce biomethane that's pretty much oxygen free. So this just to illustrate that you can actually produce biomethane that contains very little oxygen, and at least for the newer, larger Danish plants, it's actually also the cheapest way to do it. Next slide, please. So if one wants to produce biomethane that has a low oxygen content, there are three places to focus at. It's the fermenter, where it could come in with the biomass. It's the sulfur treatment, where some technologies requires oxygen being present in surplus. And it's the choice of upgrading technology and the limitations of that. Next slide, please. So if you want to produce biomethane that has a low, very low content of oxygen, it's a matter of avoiding leaks and air pockets in the biomass. And it's choosing sulfur cleaning technology and upgrading technology that doesn't add oxygen to the biomethane. And that is possible. And it's, at least when we're talking large scale production, is also economically feasible in many situations for newer plants. If the oxygen can't be avoided because of technological or historical or economical issues or whatever, then, and we don't want it to go into the storages, then the alternative is to remove it, which would normally be done catalytically. And that could be either locally at each biomethane plant, which would be very expensive, but could be done at key points in the grid or at the sensitive installations. No matter if we do it one way or the other, it's important that if we want the gas to be part of the green transition, and if we want the green transition to be as cheap as possible, then we need in Europe to decide and agree on the most cost-efficient way to handle the oxygen. And we need to do it soon. We shouldn't look at what's cheapest for the biomethane plants or what's cheapest for the TSOs and DSOs or what's cheapest for the storages or each country right now. We need to look at what's cost efficient for the gas sector in Europe overall to not end up being limiting ourselves and others and doing this in a more expensive way that will make green gas less competitive compared to green electricity. Next slide, please. So back to Denmark, we have 2 gas storages in Denmark. We have Lille Torup, that's in northern Jutland, on the left, and Stenlille, that's in Zealand. And the figure on the right shows the biomethane share in July last year. And as you can see, one of the storages is located in an area with very high biomethane production, while the other one is located in an area with quite low biomethane share. And I'll just talk a little more about each storage. If you move to the next slide, please. So first off, there's this Lille Torup that was in northern Jutland, the area with high biomethane production. It's a salt cavern storage, meaning that the general thought is that it might not have very big issues with oxygen. So the main concern from Gas Storage Denmark is that it might increase corrosion rates. And that is not something that they consider that much of a worry because corrosion has always been an issue and it's already monitored. And a slight increase in corrosion rate is not a major threat and damage can be repaired, parts can be exchanged. So that's not the main storage they're worried about. I have pulled some data for the oxygen content in the gas injected in the storage. That's shown here. And as you can see, it's higher during the summer, of course. But even with the storage that's located in a high biomethane production area, and even during last summer where the share was very, very high, there's only around 50 ppm in the gas injected. So that's also an important point here, that because of local consumption of the biomethane and because of mixing with the fossil natural gas, even if you have a high local production of biomethane, it doesn't necessarily reach the transition the network and the storages. Next slide, please. And then there's the other storage in Stenlille that was in Zealand, the area with low biomethane production. This is an aquifer storage, so there are some more worries about how oxygen injection might infect the storage. There's of course also here the increased risk of corrosion, but also worries about if it might risk microbial contamination or oxidation of minerals. There's risk of H2S production and souring of reservoir. So there are some more possible major issues there. They're mainly worried about this microbial activity that biofilm could plug the pores in the storages. The experience so far is, you can see in this graph on the right. As you can see, it's very similar to the content at the other storage, actually, despite them being in different parts of the country. And also here, there have been in summer periods up to around 50 ppm. So that's above the EN standard, but still not that high. And so far, at least, they have had no issues detected due to these levels. Next slide, please. So right now, the preventive measure, if the oxygen content becomes too high, is that they can temporarily halt injection and possibly inject more in Lille Torup, the salt cavern, if possible, to try and avoid injecting oxygen in the aquifer storage. But that's of course not feasible in the long run to just not inject if the biomethane share increases and we have to fill up the storages during the summer. So they're looking into future steps of better monitoring of oxygen levels. There's the Baltic pipe leading natural gas from Norway through Denmark to Poland that will, of course, naturally and conveniently dilute the biomethane. If all else fails, there's the option of injecting the gas in less sensitive parts of the aquifer, even though they would, of course, prefer to avoid that. And then, of course, there's the consideration of whether it's required to install some kind of oxygen removal prior to injection. But like with all other storages, they also feel that they need to know more for how to handle this and what's necessary. They are planning to do some microbial growing of some of the sand that's sometimes extracted with the gas, and looking into whether to do some collaboration with research institutes or other storage operators. But overall, their approach is quite clear that either they're part of the solution to this green transition or they're out of business, because they don't see a future in gas if they don't embrace this green transition to biomethane, because then it will be phased out. So they have a very constructive approach that they have to figure out a way to handle this and be part of the solution. And that was it for me. Thank you.
Thank you. Thank you very much, Annette. I think it was something to think about. Either you're part of the solution or you're out of the game. I think we can, but I'm not the one to moderate the Q&A, but that's actually a good starting point. I would like to, after this final presentation on the case in Denmark, I would like to hand over the word to the moderator of the Q&A session, Anne-Sophie Decaux, who is also heading the Gas Infrastructure Standing Committee in MARCOGAZ, and is also the Chiati Gas Technical Director, once you are not occupied by MARCOGAZ.
Okay, thank you, Thea. Thank you. It's now time for questions. Maybe firstly, we have a question on the chat. It was a question for Harmen. I think, Harmen, what do you call large versus small production sites in terms of cubic meter per hour?
Yes, and thanks for this question, Xavier. So large can be anything from 2,000 cube of biomethane an hour. For that, we need around 1,000 installations. Smaller ones are typically 700 cube an hour of biomethane. And for that, we need 4,000 installations within Europe.
Okay, thank you, Armen. It's clear. And don't leave, because we received other question, and one is for you. The REPower EU communication has set a target to deploy 35 billion cubic meters of biomethane by 2030, but also a specific target for 2022. Are there any particular needs to accelerate the scale-up of the sector already this year? You are muted.
I did it again, and so. But yes, there are. But first of all, I think most of the measures will be midterm, I would say, because we have the target of 3.5 extra billion cubic meters in 2022. We calculated for that we can on a organic growth path, we can already do between 0.8 and 1.2 billion cubic meters. What we need in the meantime is that the European Commission needs to approve already the mechanisms, the support mechanisms, which, for example, Italy and Czech Republic has put forward. And they've been sitting on it already from the 17th of November. So this whole process with regarding to permitting needs to speed up very quickly. But what I would like to stress is that the midterm is probably more important to accelerate. We need to solve this oxygen pathway. We need to make sure that we can inject. We do not have time. If we need to have energy security within Europe, and we would like to have renewable gases, we need to be pragmatic as well and make sure that we put in the right measures so that we can accelerate as the industry would like to see as well.
Yes, thank you, Armen. We understand the needs. We have now a question on the chat to Tim. Is Tim with us? Okay, Tim, when do you expect to analyze existing high salinity sandstone reservoirs? When does GERG analyze the sulfur precipitation effects which exist?
Yeah, it's an interesting one. Because a lot of the current work is aimed at aquifers, but clearly the water chemistry in sandstone is really quite different. So, and we've got a 2-year experimental program, so we will be getting round to the sandstone ones. Effectively, if somebody sends us some decent data as to what water chemistries are of interest, we will include them in the program because we want to do a nice wide variety of chemistries. The sulfur precipitation is interesting. It's probably an issue with H2S, so that might have to be in a future phase because our current experimental facility isn't rigged for sour running, but I mean, it could be adapted if people are particularly interested in that. We might well see some sulfur precipitation as part of the local acidification and dissolution of pyrite. So that'll be interesting because when we turn the thing on and get a load of sulfur out of it, then that'll tell us quite a lot.
Thank you. And there is another question for you, Tim. Did you follow RING's project that observe impact of oxygen in natural gas under laboratory reactors with gas, water on rocks phases with microorganisms?
Yeah, we've got a fairly close watch on that project. Our collaborators at the University of Power are extremely familiar with it, and there'll be quite a lot of interaction between that project and this project. And we're not as interested in the microbiological aspects, more the geochemistry, but the geochemical learning from the RINGS project will definitely be included in our project, and it does help us a lot with the experimental design because we're trying to do fairly similar things but without the bacteria.
Okay, thank you. I have received a question for Hélène, maybe. Hélène, are you with us?
Yes.
Okay, thank you. Is the effect of oxygen on the subsurface reservoirs expected or proven?
Yeah, unfortunately, it is proven. It has been observed in the laboratory and in some in situ injection pilot project. One of these experiments will be published soon. So it's normal because in the subsurface, the subsurface is an anoxic and reducing environment. If you inject oxygen, the oxygen will be consumed. That's normal. As it had been mentioned, carbonate may have a mitigation effect, but we have to deal with that. And as it has been mentioned, it's a case-by-case assessment that have to be done on this impact.
Mm-hmm. And what could be the next steps for MARCOGAZ on this topic, Hélène?
Oh, obviously, it's a very important concern, this oxygen and biomethane acceptance. All the EC storage operator in Europe are very active. You mentioned several research programs, and knowledge is currently growing. So the working group storage may be a very unique platform to share all this experiment and to have a common point of view. And I hope it would be possible in the near future to review and complete our position paper on the topic.
Okay, thank you. We have another question on the chat. Some countries plan to also inject hydrogen in the grids. Will it affect the impact of oxygen from biomethane? Maybe it's the effect hydrogen-oxygen.
Yes, I could give a first step of answer. It is mentioned in our paper. Some authors say that if you inject oxygen, it may have a positive impact on the environment provided by hydrogen. So perhaps, but this have to be proven. Oxygen plus injected in natural gas containing hydrogen may be positive, but
Okay. Thank you. I have a question for Annette. Annette, are you with us?
Yes, I'm here.
Yeah, thank you. How do you imagine the Danish situation will develop in the coming years? And how might this influence the Danish gas sector on storages?
Well, I think that everyone imagined that the biomethane share would increase in Denmark over the coming years, but the current Ukraine-Russia situation will probably mean that it develops a lot faster than expected, and faster than the storages originally expected. So right now they are working on faster than expected on how to handle the situation best. There's no firm plan yet, but it also underlines the need for making decisions, not just in Denmark, but overall to make decisions faster rather than later, to not end up in situations where you have to make fast solutions to stuff. From the Danish gas sector's point of view, I think one of the larger concerns is that we hope to have the Tyr field in the Northern Sea up and running again within a short period. And that will mean export to Germany with the low oxygen limit. And that will, of course, if the biomethane shares increase a lot, mean more oxygen that might have to be handled in Denmark. And with the current rules means that Denmark has an extra expense for handling that.
Okay, thank you, Annette. A question on the chat just now. Is there more or less oxygen in biomethane from pyrogasification or hydrothermal gasification? I don't know, maybe Tim, do you have the answer to this question? No?
No, to be honest. It's more a production question. Herman might have more of an idea.
It depends on the treatment. Maybe Herman.
Yeah, well, I do not have I do not have a set out a scientific proof, but guessing from the fact that it's under thermal circumstances and pressure, without oxygen there, I think it will be lower in oxygen content, probably even significant lower, but don't pin me on it.
Mm-hmm. Thank you. I have another question for Tim. The experiments concentrate on aquifer and depleted reservoir storage. Are you going to look at the effects on salt cavern storage?
That's an interesting one. What we found in the first survey, really, I think it's what Annette was talking about as well, is that biomethane storage in caverns is regarded as a lot less of a risk than the reservoirs and aquifers. And I think it's mainly because you haven't got the risk of blockages because the caverns are quite large, and well, they don't really have a pore size, but it could be blocked. So the only real risk in caverns is H2S production from sulfide mineral intrusions. And I think people understand that a lot better than the reservoirs. So we'll probably stay away from caverns for now, as people don't seem to think it's a great issue. And we'll concentrate on the more reservoir aquifer side of things.
Okay, thank you. There is another question about the blend. Aside to the oxygen challenges in presence of hydrogen and biomethane blends, what about energy density shortage after blending hydrogen and biomethane? I don't know if someone
Perhaps I can take the point, Anne-Sophie,
Yes.
if you just to what is mentioned as energy shortage, probably it corresponds to the fact that hydrogen with the same volume do not contain as energy as natural gas, as methane, roughly the third. So it maybe have an impact. As far as oxygen is concerned, it will be always only a very small part of the blending, so the impact will not be relevant. So it's more a question for a webinar on hydrogen acceptance in underground gas storage than biomethane, I think.
Yes, I think so. Thank you. A question for Annette. What specific survey Danish storage is performed to assess oxygen impact on them?
I would like to
Estimated as
answer
well?
that question, but I'm afraid I don't know. I have talked to the Gas Storage Denmark, and that's the feedback I've had is that they haven't observed any effect of the oxygen injection so far, but I haven't been told exactly how they have decided on that. They haven't seen anything.
Okay, thank you. Another question for Tim. As understood, the experimental work will be undergone under pressure of 11 bar of biomethane max. Isn't it important to test under higher pressure, for example, 60, 90 bar, similar to storage conditions?
Yeah, it's a good point. What we intend to do is, I probably didn't make it enormously clear, is the 11 bar is the partial pressure of oxygen. Effectively, or the maximum partial pressure of oxygen. So if you think of the oxygen might only there as 1%, we're actually simulating a really, really high reservoir pressure. So if we put in something like 11 bar of oxygen, assuming you're injecting at 1%, it comes out as well in excess of 100 bar total pressure, because we have to think about very high reservoir pressures. But as I mentioned, the partial pressures the key factor. Because most of the components in biomethane are effectively inert to the reservoir, so we don't need to include them. So we'll be interested in the oxygen part. So we simulate the oxygen pressure, not the total system pressure.
Okay, thank you. Maybe to finish, two questions, one for Harmen. What are the key priorities to accommodate higher shares of biomethane in the gas grids on existing gas infrastructure?
Right. The most important thing is now we have the Repower EU communication out. The target is going to be set on the 18th of May. The European Commission will detail this further. We will hopefully work together with the European Commission and the member states in a kind of public-private cooperation to make this all happen. So that is one very important item, to make sure that we are working together to achieve the goals. Another part is it needs to be within the Renewable Energy Directive. The target needs to be written in to make sure that everybody has the goal in mind where to go to.
Thank you. Before the last question, a question for Tim. Do you intend to compare the result to predictions from geochemical simulation software to assist operators in future evaluations?
Yeah, that's part of the program. We're going to before we do experiments, we're going to predict what should happen using probably the US Geological Survey Freak or similar software. And then we can see basically how accurate it is, because practically nobody's going to want to do a test every single time they ask someone asks them to inject biomethane. So if you can simulate it in software, that's going to be a lot easier for everybody. If it's successful, then we'll put that in the protocol, because the software is effectively free, so it wouldn't incur costs for the operators.
Okay, thank you, Tim. And the last question is for Annette. Based on Danish experience, how do you suggest Europe prepares for increasing biomethane and oxygen in the gas system?
Well, I think my main advice would be that if you want to avoid oxygen in the storages in the cheapest way, then new plants should be built in a way that avoids adding oxygen to the biomethane. And at least in large scale, that's also the cheapest way to produce it. But if that's not possible for economic reasons, or because there are a lot of old plants that has too high oxygen content, other solutions might be necessary. But as I said, I think the most important thing is to make a common decision in Europe and to do it soon, so that we don't end up deciding on 1,000 different ways in Europe to handle this that might end up not fitting well together and making it more expensive for all of us. And then we'll have to figure out how to split that bill somehow, but to try and agree on the best way to solve it for.
Okay. Thank you, Annette. Thea, I think that it's okay for question now.
That's very fine. Thank you very much. And Sophie, thank you for an excellent moderation of some very interesting questions for the speakers to give good and very precise replies on the questions asked. I think that adds a lot of value to this seminar. And then I would like finally to give the word to Manuel Cox, the MARCOGAZ Secretary General, in order to give some closing remarks on this session. The word is yours, Manuel.
Thank you, dear Thea. Biomethane is proven to be really a solution for the energy mix towards decarbonization of the gas system. And reaching the target set in the REPower EU is a challenge for all of us. During this webinar, we have seen good examples from Denmark, and we think that this is a good show of what the other European countries need to do and need to follow. It is possible, indeed, to produce biomethane in higher scale. On one side, and on another side, storage. We saw that storage, in fact, is an integral part of the gas grid, and it plays a relevant role not only for the security of energy supply, but storage is also very important for the functioning of the gas market. We have also seen that research and technical assessment is ongoing on storage, and this will allow developing the storage for not only for natural gas that has been in place in the past, but also for renewable and low carbon gases. We are coming to the end of our webinar, and I would like personally and also on behalf of MARCOGAZ members to thank our President Thea, Harmen, Hélène, Annette, Tim, and Anne-Sophie for these wonderful presentations and wonderful webinar. And we would like also to thank all our participants, and we would like to see you again in our next Tech Forum. So thank you, everyone, and we hope you a very nice day.
Thank you.